All right, so we're going to talk about bonding today, and we're going to talk about ionic bonding only today. And so there's some big words that you need to know. First of all, a chemical bond is an electrostatic force. There are only a few types of forces in the whole universe. Here's one. An electrostatic force is based only on opposite charges. Just like a magnet has a positive end and a negative end, ions have a positive charge and a negative charge. What has a positive charge? A cation. And a cation will be, in our case, well, in all cases, the metal. What has the negative charge? The anion. And the anion will be the non-metal, or another thing that we're going to learn about tomorrow. And remember that the universe is very lazy, and the universe favors the formation of bonds so that the atoms are more stable. They are more stable when they are hooked together than they are when they're apart. In an ionic bond, what you need to remember is it is a complete transfer. The metal gives up the electrons and the non-metal gains the electrons. The number of electrons lost by a metal must equal the number of electrons gained by a non-metal. That makes sense. Here, watch this.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons.
So I think that you can probably figure out what's going to happen next.
As the oxygen and hydrogen.
When we talk about the next type of bonding, is when they share. But today we're only talking about the complete transfer of electrons. So an ionic bond is a transfer of electrons from what to what? Metal to a non-metal. Run all over the classroom.
In living organisms, atoms are joined to form molecules by a few kinds of bonds, mainly ionic, covalent, and hydrogen bonds. Click the buttons to view an animation about each bond type. Sodium atoms and chloride atoms have unfilled orbitals in their outer shells. The lone electron in the outermost shell of a sodium atom can be pulled or knocked out. This ionizes the atom. It is now a positively charged sodium ion. A chlorine atom has an electron vacancy in its outer shell and can acquire another electron. This ionizes the atom to form a negatively charged chloride ion. The two oppositely charged ions attract each other. An association of two ions with opposing charges is known as an ionic bond. You can observe the outcome of ionic bonding in a portion of a crystal of table salt, or sodium chloride. In such crystals, sodium ions and chloride ions interact through ionic bonds.
Okay, I'm ready. It makes it seem like the only bonding in the world is between sodium and chlorine.
It's just because it's like an easy one.
Yeah, it is an easy one. I do want you to look at what happens here. Sodium and chlorine make a compound that's named sodium chloride. We'll talk about that a bunch more in just 1 minute. This table is an electronegativity chart. Remember, last unit, we just talked in general terms about the electronegativity of various atoms, and you know which one is the most electronegative?
Fluorine.
Fluorine has a value of 4, and what is the least electronegative?
Francium.
It has a value of 0.7. The greater the difference between the two electronegativities, the more ionic the bond is, the more the electrostatic force is more likely to make a bond. Wow, that came out kind of sideways. Fluorine and francium have the greatest difference in electronegativity. That means their bond together will be very, very ionic. They are very much attracted to each other. Francium really wants to get rid of that electron, and fluorine really wants it. Yes?
Why is not with XE Zion? Why does it?
You know
have
what?
a noble gas?
For reasons that are beyond the scope of this course, xenon will bond. And actually, it's not that far out of the scope of this class. If you look at xenon has a high energy level, right? Because it's farther down the periodic table. So its nucleus is unable to control the valence electrons very well. So when forced next to a highly electronegative atom, and actually it bonds most commonly with fluorine.
Are ions, do they always look like noble gases?
Yes.
So you can't have like an ion that doesn't have 8 or 0? Good.
I'm going to say yes. That's not always true, but it works for today. All right, so moving on. we saw in 2 or 3 different ways, one sodium atom losing its electron to become a sodium ion, and one chlorine atom gaining that electron to become a chlorine ion, and together they formed NaCl, sodium chloride. One compound, one unit of NaCl is called a formula unit. One package of ionically bonded metal and nonmetal is called a formula unit. Now, they don't always bond in a 1-to-1 ratio. It depends on their charge. And their charge depends on their Lewis dot diagram. Here's the Lewis dot diagram for potassium. Here's the Lewis dot diagram for sulfur. Potassium has this one valence electron to send over to sulfur when it bonds, yes? There it is. Does that complete sulfur's octet? No, it doesn't. So actually, it takes 2 of the potassiums for every 1 completed sulfur octet. You get that? The formula would then be K2S, saying that 2 sulfurs are required to fill the octet for sulfur. The way you would draw this would be something like this. When we did our Lewis dot diagrams. So these 2 things added up to form this formula unit for K2S, potassium sulfide. Huh? No, water is something else because it's 2 nonmetals, and we'll talk about that. Good question though. Properties of ionic compounds. Go ahead and write these down. Has anybody ever seen that pickle that's made into a battery?
Yeah.
Have you?
You should have seen 8th grade.
Yeah, a lot of times they do that. Do you know why the pickle will conduct electricity?
Isn't it because it's like acids inside or
Does
something?
it have water?
How do you make a pickle?
Vinegar.
And?
The cucumber and
No, not, does it always taste sour? They put it in brine. Brine is a salt solution and there is vinegar in it, so it is sour. But the 2 things conduct electricity. The salt helps a lot. Salt, when it's in a solution, will conduct electricity. Salt from your salt shaker will not conduct electricity. Has anybody ever made caramel? You take sugar and you cook it. That's all caramel is. Did you know that?
Yeah.
And then in America, they put milk in it. And in Europe, it's just the sugar and that's heated. It's much more delicious here, by the way. Sugar has a very low melting point. It doesn't take a lot of heat to caramelize the sugar. Have you ever tried to caramelize salt? No, because you really can't. If you put salt in your pan and put it under high heat from your stove, what's going to happen? Not much. It will stay salt because it has a very high melting point. Ionic compounds are hard solids. All ionic compounds are solids. They have a crystal lattice structure. Does that mean anything to you? No. Did you use connects when you were a little kid? You know what connects are?
Those little
Okay,
balls.
yep. This is a connect that we're going to call a crystal lattice structure. Each one of the little balls, the connector bits, are ions. And that's the way an ionic compound is. If you took yourself down to a really teeny tiny size and looked at one crystal of salt, that's what it would look like. All right, here we go again. I showed you this just briefly in the potassium sulfide, but here is the sodium, and it's neon, it's a noble gas electron configuration. Here's chlorine in its electron configuration. We clearly see that sodium would like this to go away, that one electron, and chlorine would like very much to take that one electron. Right? Same thing for potassium. It has the one. When it loses its an electron, it becomes a cation. Chlorine picks up that electron, it becomes an anion. Together they form the ionic compound that we know as potassium chloride. Okay. We talked about this just a little bit yesterday, that there are two types of metal, a monovalent type 1 metal and the multivalent, meaning many charges, metal that are the transition metals. Okay, you need to know the different types of metals for a couple of reasons. First of all, you need to know how many electrons that each one of the atoms is going to lose to become a cation. And secondly, you need to know how the charge of the atoms, so cations, so you can name them properly. Yesterday, we talked about these special transition metals, and we remembered them as ASCA, and we talked about Harry Potter and where Sirius Black was in jail, and he was in jail in Azkaban. And that's the way we're going to remember these monovalent, these transition metals that only have one charge. We also notice that they kind of form a stair step, don't they? Where this would be silver, this is cadmium, this is zinc, and this is aluminum. And we go up in charge, +1, +2, +2, +3. It is absolutely vital that you are able to look at a metal and determine the charge of the monovalent cations. A type 2 metal is multivalent, and type 2 metal is all metals that are not type 1. They can have multiple charges, and we'll use this when we start naming. But before you name, you need to be able to write a formula. Please write down these instructions for writing formula for binary ionic compounds. Not quite sure what I'm supposed to do with this. This is one I did not hyperlink. Oh, there we go. Except that's too little to see, isn't it?
Do the thing where you press A and make it bigger.
No, because I'm actually, look what I'm doing.
Oh.
All right, we'll leave this alone for right now. Play with it later. Okay, can I find my tab? Yep. All right. So here you go. when you combine, you don't have to write this down, you just have to watch what happens. When you combine atoms, you use the oxidation number. Remember, the oxidation number is the charge, and we went over that yesterday, to help you figure out the ratio between the metal and the nonmetal. Magnesium is in group 2, so it has a charge of +2. Chlorine is in group 17, so it has a charge of -1. When we write the formula, you write the atoms over again, and then you crisscross just the number of the charge, and not the sign, just the number of the charge to the opposite atom. So this would be 1, and this would be 2. Remember that chemists are really lazy, so they never write the number 1. The proper formula for magnesium chloride would be MgCl2. That shows you the ratio. For every 1 magnesium, there are 2 chlorines. Magnesium and oxygen have the same oxidation numbers. So when I crisscross, I would put 2's by each one. Just like in math, we reduce. Can this be reduced? Yep. It becomes MgO. And that shows you that the ratio of magnesium to oxygen is 1:1. The formula unit MgO is called magnesium oxide. Try aluminum oxide on your own. You are correct, if this is what you put. Remember, for the, stand up to do this. For the transition metals, the oxidation number varies, and you need to know what it is before you can write a proper formula. Write aluminum and sulfur right now. Start by writing the oxidation number of the cation and the oxidation number of the anion, and crisscross. Sodium and oxygen. Ready, set, go.
Thank you.
All right. We skip ahead to see how far we're going. Okay. Done? That's fast. Thank you. Yeah. Good, thank you. All right, write this down, and then we'll be one step ahead for tomorrow.